हाँ मैं अभी पॉज कर देता हूँ मैं.
Yeah. Okay.
Start.
Respected senior members of INS and friends, I once again welcome you all to the INS webinar, the 15th in the series, and yet another important topic critical to atomic energy. It has been a practice in INS to invite eminent speakers and executives in the field of nuclear science, engineering, and allied subjects of public interest to know from them latest development, milestone, accomplishment worth public appreciation. Today we have with us Shri Jitendra Srivastava, Chairman and Chief Executive of Heavy Water Board. On behalf of INS and on behalf of webinar subcommittee, I welcome you, sir. Today he is going to speak to us on Saga of Heavy Water Board. Sir, you are in occupation of a very important position in Heavy Water Board, which has made the department proud of the achievement. And I intend to share my own experience doing a small work for Heavy Water Board. That is when I joined BRC in early 80s. My very first job was to investigate the multiple failures of purlin in the Tower of Kota. So that was a very successful work that I did. And thanks to Shri Hiramat, who was the chief of Kota at that time. And I must confess that that was a very successful investigation and actually taught me how to carry out a scientific investigation and the root cause analysis. If Shri R.S. Yadav has joined today's webinar, I think he will remember this work because I did it along with him. So it is a saga of ppm to metric ton, a scale that can be fit by a logarithmic or exponential development. The Heavy Water Board has rightly worked with the spirit of Atmanirbhar right from the early 60s. So today, Heavy Water Board has diversified itself into several sectors through sheer determination to convert all setbacks into an opportunity. So let us hear from Shri Jitendra Srivastava, the saga of the Heavy Water Board. And before I request Ramanamurthy to introduce today's speaker, I request our President, Shri S.K. Mehta, to give his opening remark.
Thank you very much, Srivastavaji. Very, very hearty welcome to INS platform. It's very kind of you to accept this invitation. My association, as I said earlier, was that right from our neighbor, Heavy Water Division to Engineering Division. And we had a common interaction, as Ramarao has said, in many of them. I recall when Deshpande was starting the H2S technology, we were all asked to be careful and we were trained how to handle the H2S leakage and all the things that were there. So all these things happened from the stage where Santakumar will recall that every progress in the heavy water PHW or the power station were there that non-availability of heavy water. To the stage we have come to the export of the heavy water and different technology all the things. So it's a great achievement in terms of the Atmanirbhar. I heard Sharma ji some time back. I'm happy that today we'll be hearing from you all the achievement that is going to be have been done so far. And it will be of great interest to all the INS members. So again, welcome to you to this platform. Thank you very much.
Thank you, sir. I welcome all the respected INS members and who are connected with this virtual.
Just give me a minute. Let me introduce you to the forum before we proceed.
Okay.
And so very briefly, it's my pleasant duty, good afternoon to all. It's my pleasant duty to introduce Mr. Jitendra Srivastava. He is an outstanding scientist and currently chairman and chief executive of the Heavy Water Board, an industrial unit of the DAE. As Chief Executive, he is responsible for the smooth and efficient operation of heavy water plants and other facilities located at Kota, Manuguru, Thal, Hazira, Baroda, Tuticorin, and Talcher. Shri Jitendra Srivastava graduated in Chemical Engineering with honors from the Department of Chemical Engineering and Technology, Punjab University in 1985. He joined the 29th batch of the BRC training school. He worked at heavy water plants Kota and Maniguru and held various positions such as shift engineer as he gradually went up the ladder, shift engineer, shift superintendent, deputy production manager, technical services manager, deputy general manager, and finally chief general manager. He made a major contribution towards stabilizing the operations of the first indigenous H2S based heavy water plant at Manuguru. It was a first of a kind plant involving the handling of 200 metric tons of highly toxic H2S gas. The challenge was successfully negotiated with respect to all major issues, including aspects related to safety. Engineering measures and modifications carried out resulted in an increase of 40% of production of heavy water, as well as a drastic reduction of specific energy consumption from 45 gigajoule per kilogram to 32 gigajoule per kilogram. These engineering changes still today remain a hallmark of the heavy water program of the country. He assumed charge of as Chief General Manager Heavy Water Plant Manuguru in 2016. In this capacity, he was responsible for the optimization of the operations of India's first indigenous O18 plant, and he also contributed immensely towards the production of the B4C Boron Carbide pellets required for the second stage of the Indian nuclear power program. In November 2019, he assumed charge as Associate Director Heavy Water Board Mumbai, was then elevated to the position of Director Operations, and subsequently has now taken over as Chief Executive Heavy Water Board in August 2020. He is a recipient of several awards from the Department of Atomic Energy and from other forums. So with this brief introduction, now it is my pleasure to welcome Mr. Srivastava to come forward and commence his presentation. Mr. Srivastava, please.
Okay, sir. Thank you, sir. So at the outset, I welcome all the respected members of INS and whoever have connected to this virtual meet. I welcome one and everyone. And I would like to thank Dr. S. Mehta, President INS, and Dr. A. Rama Rao, who has given me the opportunity to participate on the 50th INS webinar series. The topic of my talk is the saga of heavy water board. Many heavy water board pioneers and our leaders have given many talks on this topic. Here I would like to mention that this success story of heavy water board was possible due to untiring efforts of our leaders and pioneers who took up the vision of Dr. Homi Bhabha as a dream and made this dream to a reality. So my talk will be short. I will give the present status and I will talk a little bit more about where I have worked and some of the diversification which heavy water has taken up. So it has divided Indian heavy water scenario and diversified activities of heavy water board. I start with the Bhava Vision who has given the statement government should explore immediately the possibility of utilizing cheap hydroelectric power in India for manufacturing heavy water on one hand for our own requirement in pile and on the other hand for the sale to other countries. Actually, this they had given in the context when the after independence, the Bhakra Dam was under construction. And at that time, he has realized that once this dam will be completed, there is not such much demand of power in India at that time. Even the transmission line was not there. So he wanted to utilize that power for the manufacturing of the water. Here I want to mention, sir, I was the last in charge of that Nangal plant, which I administratively control from Kota. Every month, once or twice, I have to go to Nangal. In 99, I feel, and 2002, with this plant we have decommissioned. So whatever literature were there, I have gone through. On that basis, I will tell you their experience, how this plant has come up, and how it operated, and then when it was decommissioned. So this plant was set up with the vision of Dr. Homi Bhabha, who convinced the then Prime Minister Pandit Nehru in late 50. The technology was based on the electrolysis of water and subsequent cryogenic distillation of enriched hydrogen gas. When this concept was they taken as a on the paper, then they found out that a lot of hydrogen is available. What we will do of that hydrogen? Then finally government decided, they have given the task to FCI to install a fertilizer plant over there. And there will be a heavy water plant. After electrolysis, they will produce the heavy water, and whatever hydrogen will be available, that will be utilized for the manufacturing of the fertilizer. Then the FCI plant had come up there in the Nangal. There was a huge, there was a 3-stage cascade electrolysis, and third stage, whatever hydrogen was coming out enriched in deuterium was going. The flow rate was around 5,000 nm³ per hour, and the total power consumption of that electrolysis was around 140 megawatt. And it was written there in the documents that at that time it was the biggest electrolysis plant in entire Asia. Then this cryogenic distillation, the turnkey project was given to the Messrs. Linde, Germany, who has installed there a cryogenic distillation plant. When I gone there, the beauty is this plant was based on the cryogenic distillation on 3-tier refrigeration cycle actually. The first cycle was the ammonia cycle, where with the help of ammonia cycle, they were able to achieve -40°C temperature. And the second cycle, refrigeration cycle was the nitrogen refrigeration cycle, where the nitrogen was compressed at 160 kg pressure, pre-cool -40 with ammonia and the return gas of this nitrogen. And finally, the Joule-Thomson, they were achieving the liquid nitrogen, and we were able to achieve the 77 Kelvin temperature in that liquid nitrogen bath. And the third refrigeration cycle was the hydrogen refrigeration cycle, where the hydrogen was compressed up to the 70 kg pressure, and then pre-cool with ammonia and then liquid nitrogen bath and the return gas of hydrogen. And then it was the Joule-Thomsons, and they were achieving around 21-22 Kelvin temperature, where the hydrogen was liquefied. So this was the plant, and the total capacity of this plant was 14.1 metric ton per annum. It was running successfully But mid-80, there was a strong demand that this we should not take up of so much of power from Nangal because the country need power. So in mid-80, they have stopped all the electrolysis of water. Then heavy water thought how to, and then the total power consumption for the cryogenic distillation was around 3 megawatt only. Then heavy water thought how to run this plant without the electrolysis. Then at that time, FCI, which was later on renamed as NFL, they have expanded. They had one stream of the naphtha-based hydrogen. So heavy water thought whether we can take the hydrogen from the naphtha plant or we can operate this cryogenic distillation. They found out this the impurities level actually to achieve the liquid hydrogen is the purification is very important. Because all the impurity has to be removed, otherwise it will entirely choke the plant. But this plant, this Nangal plant, refrigeration plant, it was able to take up the 10 ppm impurities level from the hydrogen. But the impurities level of the hydrogen from the naphtha-based plant was much higher than this plant. Then the economics was worked out. And then finally, they have taken up a stream of the hydrogen from the naphtha-based plant and put up a PSA-based purification plant. And from that PSA, after getting the through PSA, the initial purification and the impurities level was coming less than 10 ppm. And they operated the heavy water plant. But as this deuterium level had come down from this naphtha-based plant, then the capacity got reduced from 14.1 metric ton to 8.6 metric ton. But overall, it was economically viable and they have operated till 2002. And then it was decommissioned and dismantled. So this, when I have taken their advice that capacity was 8.6 metric ton, when I seen that plant, actually the first beauty was there, the entire plant was total manual operated actually. There was no control valve in entire plant. Even the critical operation of Joule Thomson in all, from the cold box to the control room, the long stem ball coming and the the handle was there in the control room. Direct tubing was coming. It was showing the pressure within the pressure gauge, and they were operated that valve. And more than 40 years they operated with all manual, with high pressure manual, and very successfully. And I had seen the dispatches from that Nangal ki heavy water. It has partially supported, entire dispatches has gone to BRC to support the research reactor at that time. Then the second plant had come in existence in Baroda actually. Baroda, it is monothermal hydrogen ammonia exchange process. It is a very complex technology. I will not go through, there were so many problems in all. And but this plant was operated successfully up to July 77 actually. July 77 it was started, and 98 is what discontinued because it was connected with the GSFC. GSC had changed the technology and they have gone for the medium pressure, and the pressure got reduced of the syngas. Then the continuation of operation of this plant was not possible. So this plant operation was discontinued in 1998. After 98, it was thought that there was one technology, water and ammonia exchange process, where the source of deuterium will be the water. This was a technology which we have not demonstrated so far in our heavy water, all the heavy water board program. So we have demonstrated this technology and successfully it has run. It was disconnected from the GSFC there was the ammonia water exchange, and we could produce on the continuous basis 4-5 years the heavy water. But because the specific energy very high, the cost was very high, and when we have discontinued, then we call it but that technology was established, it is successful. If new ammonia based plant will come, it can be put as a front end technology this, so that the production of the ammonia plant can be enhanced in the future course. Subsequent to shutdown of heavy water, diversified products like K-metal, TVP solvent, and lab scale production of deuterium level compound and NMR for solvent is also carried out in the Baroda plant. Baroda plant and Tuticorin plant, they were sanctioned together actually, and this was also struggled a lot, 49 metric ton of the capacity of this plant. It was connected with fertilizer plant SPIC. SPIC had suspended their operation because the SPIC was based on the naphtha based plant, and in 2007 the cost of naphtha had gone very high, and it was not possible to operate the fertilizer plant, and they suspended their operation. Then we have to go to shutdown of this plant. But now recently the SPIC has restarted after availability of the natural gas from Ramagundam, and we have taken up to restart this plant, and it is expected in 2024 we will recommission this plant of Tuticorin. This heavy water plant quota actually, this was my Karm Bhumi quota. At 29 years, I worked started my career from SOC to Deputy General Manager. As Sharma ji, everybody talked, the selection of the process. Actually, when I joined in 86 there, all our leaders like Sharma ji and all, we have shown this is the process we have to get successful. Otherwise, the Indian nuclear program is not possible. Because this process has produced more than 90% heavy water by this process in the world. Because it is not parasitic in nature, large amount of plant can be put because the raw material is the water. But the technology is not so complex like ammonia. But the problem of this plant is we have to handle the large amount of toxic H2S. The safety issues are all the equipment selection, and the second thing is the system is very highly corrosive. Material selection was very important. So when there was a heavy water division in the hall 2 earlier, we have heard there they have put a pilot plant, and for this plant actually nowhere even the thermodynamics was not available. Everything they have developed in the hall 2, and the plant was selected for the Rawat Bhatta because their reactors RAS 1 and 2 are coming up, and there was a provision for the excess steam generation from the core of this RAS 1 and 2, and that was designed only for the heavy water. That is the selection was done there. So this plant it actually was sanctioned back and started, but because of the Pokhran 1, it has delayed. Even the RAPS 1-2, the Canadian has gone back, then Indian has took up the construction of this plant. All some imported item which has to come, there was a ban. It took a very long time. Then this plant came very late actually. Even RAS 1-2 and heavy water both came very late. When it was conceived and the construction started, and when it was commissioned, there was a long gap, if you will find. That is because of the Pokhran 1. This plant actually, when we started, I told you it is a very challenging actually. The H2S which we were operating when we were doing in our college lab, we think it is nothing, but then we realized how dangerous it is and how corrosive is this. So this plant was operating, but it was operating in not on the sustained basis, and some of the some amount of production were taking place, but nobody can say that we have succeeded this process. And we were taking the one factor that we were taking the steam from RAFs 2 actually. RAFs 1, right from beginning, there was some problem, and later on there was a crack in the end seal and it was closed down. So RAFs 1 was not operating, only one plant, RAFs 2 was operating. And they initially, on all the plant, there is a teething trouble. So once the RAF trips, then we are also going to trip. Then again to recharge the steam of 1.6 kilometer long line, it takes more than one day. So this process was going. Actually, if a new process, if you are developing in any plant, so once the plant runs in sustained basis, then you face some problem, then you can analyze and you can find out some solution. But even the plant is not running on the sustained basis, so problems is coming, but we could not visualize, or we could not experience, or we could not observe. So that is why all the problems took a very long time. Later on, there was a big problem because RAFs 2 was having the sagging of the tubes actually, and they have to go in the permanent shutdown. Then it was decided by Heavy Water Board, our pioneer, that we should go for the steam generation plant at Kota. And we put up a steam generation plant in Kota. And then we got the sustained basis, the steam, all the operation issue in that period. And I tell you, in a very short period, we have all issues were addressed, and plant run by 91, 92, we produce a large quantity of heavy water, and we declared this heavy water plant Kota as a success. Then this Talcher plant actually, this plant actually was also connected with FCI, and FCI was also doing the first time the gasification of the coal-based plant actually. And this technology is the ammonia-based plant, ammonia hydrogen exchange, but it is a bi-thermal actually. So here I want to emphasize the things our leaders actually they have worked all technology. The beauty of this process is this that the specific energy is very low. But I think I don't remember in the world anywhere it has plant operated. But India has also struggled 20-25 years, but that was not the sustained basis supply of steam from the and hydrogen from this FCI, and the internal problems were also very high. That finally that it was decided to close down this Talcher plant. Then the Thal, actually whatever problem we have faced earlier, Baroda and Tuticorin, now we are confident that heavy water plant Thal was based on ammonia-based plant, and it was connected with RCF. This Thal, Hazira, and Manuguru, these three plants were sanctioned together actually. And Thal and Hazira has come, and it was operated. Thal commissioned 87, and nicely it has operated and produced as per the design capacity process. Similarly, Hazira is also produced as per design, even the better than design this Hazira plant has operated. And at that time, the Manuguru plant has come in picture. And actually the beauty of this is the only plant actually I can say in all our 7 heavy water plant, Manuguru is plant, we are not dependent to anybody. We are just taking the coal from the Singareni coal mines from a 10-kilometer long rope-based system, and water we are taking from Godavari, and in-house we are producing the steam and power. So it total is in our control, and this plant when it was commissioned, the experienced manpower from Kota also contributed here, and in no time they have it come under full capacity in the very, and they started from full capacity of this, and it was a double capacity plant of 185 metric ton per year. When
बदमाश है
producing Then we declared, and we were surplus in heavy water. And the Bhava dream was to explore the heavy water. Export a heavy water, we thought, but we should be competitive in nature, because all these heavy water plants are the energy extensive processes. So I still remember Mr. Kamath was the chief executive, and there was a long drive actually in all the plant to study each system in house and find out what can be done to reduce the energy. And numbers of modification every plant has done after due deliberation, and the specific energy had come down. I show the curve here, which we were running at 44, 38. Finally, we have come on 30, 31, 32, and we were internationally competitive. And first time we export to South Korea at 100 metric ton of heavy water. And there was many times we exported to South Korea. Then we have given 100 metric ton to the China and France and then America. So I can say the vision of Bhava, actually that was taken as a dream by our leaders, and with their efforts, untiring efforts, it has come to reality. And Bhava had given the vision at the time when not a single drop was produced. We have to export. Actually, he was such a visionary, and that has come true. It's a beautiful journey. It was very challenging, but it was very successful. And I enjoyed at Kota. Actually, Kota was a very remote place. And when we joined, even the television was not there. Antenna-based television was all over India, but the Rawatbhatta was not there. And the scooter was not there. So, but we were all the bachelors, and we enjoyed that journey. So here in this given key 14 metric ton was added in 1962. In the Baroda came in 45 metric tons. So if you see key here is the maximum around 550, 580 metric ton was the capacity. And now we are running at this place after losing 49. We are fully prepared to give them whatever they have given us their program up to 20 to 32. We will supply the untreated heavy water requirement to NPCIL. This taken the diversified activities. This is the one of Boron Carbide for fast breeder reactor, nuclear grade solvent for fuel cycle, nuclear grade sodium for fast breeder reactor, and metal grade O18 for PET scanning. B10 enrich, actually the 65% is required for CSR and DSR for prototype fast breeder reactor of Bhavni, and as poison and control rod, and 50 and 90% IP B10 for fast breeder test reactor of IGCA. Production process mainly involve the B10 enrichment using exchange distillation of the boron ether complex, and then conversion of this BF3 into the complex of KBF4. These two processes is taking place at the Talcher plant. After KBF4, then it is going to the Manuguru plant in the electrowinning system, and they are making the KBF4 to the elemental boron. Then the elemental boron is taken out, it was micronized and the purified, and then it was mixed with the carbon, and in the high vacuum induction furnace, it is converted to the boron carbide. And then in the hot press, it was pelletization, and the sampling machine, it is getting finished. Actually, this technology, here I want to mention, the BRC had given technology, and on the industrial scale, we have done in the Kota and Manuguru and Talcher plant. Recently, heavy water plant Manuguru supplied. Actually, this the quality control was very tedious of this actually, and there we are like actually we are strong in the chemical, but the structural strength. This was the new for us also. But because Manuguru is very near in the Hyderabad, and their facilities are there to check the things of the strength in all. Finally, it was successful, and they have accepted our around 120 pellets of 50% IP B4C pellet. Total weight is around 15 kg. It has was and it is given to the NFC for the manufacturing the control rods. This is the actually flow diagram. In the Talcher, we are enriching the boron and converting to the KBF4, and Manuguru, we are doing the making the elemental boron purified and then converting to B4C induction in the induction furnace, and the pelletization and the fabrication of control rods in the NFC. These are the this is the plant at Manuguru. It is the electrowinning process. This distillation column is at Talcher. The nuclear power plants, actually this solvent needs the solvent front and back end of the this were imported earlier. So heavy water board, actually Talcher plant were not operating, and the skill and very experienced manpower was there. Then this new diversified activities in initial stage were taken up at the Talcher plant for production of solvent. And no doubt the initial, whatever the technology on the lab scale, we are coordinated with BRC, and they have given us, and we have on the pilot scale and then further industrial scale that we have done at the Linger plant. Talcher plant. Boric acid enrichment for making B10 enriched B4C pellet and BF3 gas production process is established. These are the actually given in the Talcher plant activities. So BF3 gas production process is also established there, because this BF3 gas is required for Milgauss neutron detectors and required by ECAL. So this Talcher plant has these are the had TVP. Actually TVP we of industrial scale with Talcher we run, and then finally we augmented in the Baroda plant. And this is the main solvent which NFC is taking as a large quantity every year, and we are producing. And we are in the small quantity, we are also produce Tapo, Topo, DAFA, GNPPA, and Calis Crown 6. Actually, these other we are making at a small scale actually right now. Whenever there is a demand from the BRC or IG car, we lab scale we produce and give up. What we are bringing a versatile plant of solvent production at the Tuticorin. There we have further augmented the production capability at Tuticorin plant. So this Baroda plant, right now Baroda plant is nuclear grade sodium. Actually, they have taken up the developmental work for the cell for the sodium production. So this 2 kiloampere, a closed cell, this was run, and around we have produced around 7 metric ton of commercial grade sodium metal. And working principle is the closed down cell technology, and this is the economic mixtures optimally with a lot of permutation and combination. Found out this is the best combination, and that 7 metric ton we have produced commercial grade. The 2 kiloampere cell was operated in an efficiency of 50%, sustained manner. Purification unit. This purification unit actually the technology was given by IG car. Here we run the purification unit, and around 3 metric ton we have consignment via IG car, and their feedback has come. It is meeting all the requirement of nuclear grade sodium. Then we have taken up the to operate to enhance the capacity of 600 metric ton per annum sodium production at Baroda. So this 2 kiloampere cell we have scaled up as a 24 kiloampere cell. That was the 1 electrode configuration. Here is the 4 electrode configuration, and it is one prototype to cell is already ready, and we are about to start in 2-3 months. And building of 600 metric ton sodium is also ready. Only the further, once this is successful, then we have to multiply this cell in that building actually. But we are just waiting to operate some time. So if there is any problem, any changes are required, then the further order will be given on that basis, and we will produce the 600 metric ton sodium at Baroda. This oxygen isotope 1618 natural abundance around 99.76 and 0.2% actually. And when we produce the heavy water, this 0.2 is enriched to 0.4% actually. So it was thought that there were many methods to produce the, if we go for in the literature, there is a many method. One method is the natural water and some liquid oxygen. You also can produce the O18 and some all other methods, carbon dioxide, NO2, something is there. But we thought that we have to take the feed as our heavy water, because we have a lot of heavy water which has the enriched double of the quantity which is the natural abundance. So this there all as a literature, whatever was available on that basis, we have taken up the heavy water board the challenging task to take the industrial scale of 10 kg per annum S2O18 production. It was deploying at Manuguru. This is the plant, right side is the plant of the S2O18. There's a 10-stage cascade, and the final product is the D2O18 actually. Even if we operate with natural water or we run a D2O, but final product will be the D2O18 actually, if in this cascade. So finally, the medical protocol we have to give the S2O18. Then we have to electrolysis of this D2O18 and break O18, and O18 has to recombine with the pure hydrogen and make the S2O18. The challenges which we have faced in this, the suppression factor is very low, in the order of 1.006. To achieve this cascade is required around 3,000 theoretical quantitative stages. High inventory is required, and thus the equilibrium time is also very high. And as the cascade go in the enriched form, then the flow rate becomes very low. Initially, it is 1.8 kg per hour, 2.003 kg per hour. And to select the pump for such a low interstage flow transfer was also a challenge. Column size initially is 20 inch to 1 inch dia, around 30-35 meters cylinder column, and adiabatic operation. Development of the contacting devices, distribution and redistribution for the lower diameter column, maintaining the cascade inventory at minimum level, development of electrolyzer for production of high purity oxygen. Actually, this I am telling you this, even electrolyzer is development is very difficult, because this is not only electrolyzer with compressor. Actually, it produces with back pressure of 4 kg. Because the amount of O18 will be so low, you cannot compress further to run for the recombination. So this electrolyzer is the electrolyzer compressor, is give the oxygen at the 4 kg pressure, so that we can inject to the recombination unit, which operate at around 0.5 kg. And development of the catalytic recombination system to produce O18. So these are the actually Dixon ring packing, which is in the high stage column. We have put it is phosphor bronze, and this is the structure packing of phosphor bronze in the large dia column. And this I have seen the electrolyzer, which give the oxygen O18 at the 4 kg pressure. And these are the circulator of the of hydrogen. Actually, hydrogen has to be recirculated, and we have to inject a slow rate this oxygen, that the explosive mixture should not form. And these are low diaphragm pumps with the metering, and the measurement is also coming there. This commissioning was system was commissioned at Manugur in July 15, and the 10% enrichment achieved in the January 17, 50% enrichment achieved in 18, and the 75 enrichment achievement in November 18, around 95.5% in the March 20. And 97 enrichment achievement in the July 20. Actually, we have to give the S2O18 at 95.5%. So we thought we have to go for 97, that there will be some dilution in the system, then it will be possible. So in the 17 January, we have this was produced the S2O18 of 95.5%, small quantity, and we chairman and secretary was inaugurated that day. And the Tuticorin plant, I told we restarted. Hello.
Yeah, please go on, Mr. Srivastava.
At the Tuticorin plant, actually, the initially O18 initial pilot scale study was done at the Tuticorin plant, and solvent production plant and the front bank at the versatile solvent production plant is coming up. It is going to commission within 6 months. And solvent extraction plant for extraction of the rare material from phosphoric acid, that plant is we have also taken up the activities and restart of activities of high water plant. These are the plants. Actually, we have taken the pictures in some of them in the nights. This is the control room. Thank you, sir. I think I have not bored up.
No, not at all. Raman, can you take questions, please?
Yeah. Thank you, Mr. Srivastava, for that very comprehensive presentation of the journey of the heavy water board, commencing very early, as you said, in 1962, with a fully manual plant, and then moving on to very sophisticated high capacity plant at Mangaluru, and then diversifying to so many other areas such as boron carbide, solvent, sodium production, and O18 production. I'm sure that people will be are much enlightened about the activities of the water board. It is now time to throw open the forum for questions. Anybody would like to ask any questions, you can please pose it to Mr. Srivastava. You may please raise your hand, and then if I can.
Yeah, can I ask Manchanda here? Can I ask a question?
Yeah, sir. Please go ahead.
Srivastava, it was an excellent presentation. In fact, not only you are helping the department with heavy water, you are doing so many things actually for fast reactor program, for fuel cycle, both front and back end. I think we are extremely proud. In fact, I think soon your name should be changed actually. You are doing so many activities actually. So my question is basically, sometime back, maybe about 8 to 10 years back, work was started at RCF for uranium recovery. If it is not a classified thing, can you share some of the information from phosphoric acid?
Normally, actually, we don't talk on this Google platform, but I told the one plant we have taken up in the Tuticorin, which I speak for the extraction of the rare material from the phosphoric acid. A new plant we have taken up at the larger capacity. That plant has whatever it was operated it was successfully operated, and the technology was established, and finally it was closed because the phosphoric production was stopped by the RCF.
Okay, thank you.
I can see Khilani. Yeah. Mr. Khilani wants to ask a question. Go ahead, please.
Very nice presentation, Jitenji. It was very nice to hear about recent developments and all you have achieved in heavy water board. I just wanted to know what is the status of the deuterated compounds you had taken up studies with ICT, as well as I understand with MS University of Baroda, as well as some interesting work you were doing on depleted deuterated water. Can you just throw some light on that, what is happening on that area? Thank you.
Thank you, sir. Actually, MS University, we have actually this heavy water board working is new for me. I am the field person actually, and this bureaucracy. Finally, when I took over in the August as a chief executive, the first mail I got from chairman, what is the status of the MS University actually? So we were right from beginning, many years back when the Mudli was the chairman, we have given the MOU form to the DAE. Then DAE has told me, no, you cannot go for, you go in the work order actually. So finally we have gone in the work order mode, and the work order is around 1.3 crore of this MS University. So it was in the C powers, but this was on the nomination basis. So it has gone to the tender committee actually. Tender committee is through it. Then 2 months back, I have given the work order to the MS University, and they are working on that project of MS University. And the other project was with the ACTRAC actually. That work order is still pending because that is around higher amount. It will go, so it is in the DAE actually. ICT, there is no project actually as such. They have proposed for 6-7 projects, but in the board actually, the JS finance was having the selection of your selection process of the party is not correct. So you have to work out, you have to go for the expression of interest, then the people will give, then only this, you are not following properly everything you are giving on the nomination, it is not correct. So that is why ICT proposal was not finalized, and we are in the process to making an expression of interest. The people will send, then the committee will evaluate, then only we can go through this process. So they told me, the earlier you are taking this type of project, this is not in order of the government procedure.
Oh, I see. So a lot of hard work you have done. I can understand. I can really appreciate the efforts you would have put to place these, things in order. But this is, please keep it up, because this is a very challenging and very encouraging field. And if you can get some results for heavy water, it will be, very, 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 very nice. In fact,
I have done actually DDW you are talking about. So DDW is 125 ppm actually. Finally, we got a DE order ki effluent we can sell. The C having the power of 20 lakh rupees.
yeah.
So how to evolve the cost of this DDW actually? So ki earlier this was around 10 rupees something paisa. It was we are selling this, but our new IFA told me ki you evolve explore the price. Then we have floated one tender of the for expression ki who wants this heavy water DDW at what cost. So 6-7 party quoted actually, and the highest was the 17 rupees. And now we are selling this DDW at 17 rupees per liter.
So let me once again congratulate you, Jiten. You have got 70% higher amount for the department. Hearty congratulations to you. Thank you, Jiten. Thank you for a very nice and lucid presentation. Thank you.
Any other questions, please? Questions, comments, observations? Sir, please unmute.
There are two stalwart of heavy water are here, Sharma ji and Kamath. Maybe they would like to make some comments on the normal observations. We should invite them. Sharma ji?
So, Mr. Sharma, can you please respond?
Mute, sir. Can you hear me now?
Yes, sir, we can.
Well, see, I have not commented because I just had the webinar, and what Mr. Jitendra Srivastava has done has detailed all the things and brought it out very nicely. It was quite a comprehensive presentation, and well, the field is so wide, and it's very difficult to cover everything in the short time that one can take for this one. Only thing is that I feel that the future, well, as somebody had commented, and Mr. Srivastava also said, now it's a position that the Heavy Water Board makes heavy water too. It's the future lies in the other activities, because on the heavy water side, we have done all that was required. And it's the other areas that where we have diversified, and like whatever is the usage of deuterium, heavy water would be the source for that. Like Mr. Kelani very rightly said that he inquired about deuterated medicines. I believe that's a very wide field, and a very, very wide field. And Mr. Jitendra Srivastava has already said that we are well off and we can meet all the requirements for the next 1 decade. And beyond that also, I had mentioned that we are quite capable of spending. So heavy water is very well taken care of. It's the diversified activities and the deuterium which is the future. I think since I had already exhausted all my points in my talk earlier, so this is all I have to say, but I want to compliment Mr. Srivastava. Done a very good job covering the field. Over.
Thank you, sir. May I now request Mr. Kamath? Mr. Kamath is there? Sir, can you please unmute? Sir, can you please unmute? Kamath, sir, we can't hear you. Can you please unmute? I think he is
Right.
able to hear us, but he is not. Kamath sir, can you please unmute? Call karo Kamath sir.
So till such time that Mr. Kamath comes online.
He's
I can
online,
ma-
he's speaking, but we can't hear him.
Okay, I just want to mention 2 points.
Yeah.
Mr. Kelani had come online and he gave some comments. I want to mention that Mr. Kelani is the father of O18 program. He's the one, he has been very modest and is not mentioned. He's the one who had done all the design. That's one. And okay, now I think Mr. Kamath has already come, so I will mute myself.
He's there, but he is not unmuted. And as an admin, I can only send a request. I can't unmute him. Somebody sent me a message.
Are you able to hear me now?
Yeah, yes, sir. Yes, sir. Please.
Speak.
Ahmad sir, please go ahead.
Are you able to hear me now?
Yes, very clear.
Yes.
Very clear. Okay. You see, as I was listening to the talk by Mr. Srivastava, the entire story of heavy water unfolded starting from Nangal to the latest H2O18. I think he has brought it up to date. But my question is, what are our future plans? What is the next thrust area for the heavy water board?
Sir, we said presently we are working on cobalt and nickel recovery from.
I can't hear anything.
Sir, presently we are working on the cobalt and nickel recovery from the Midhani scrap and gallium recovery from bare liquid. That our work is going on in the TDB plant in the advanced stage, and we are going to put up a small unit. Gallium recovery from bare liquid.
Sir, do you want to ask something more or add anything?
Am I audible?
Yes, sir. Yes, sir, you are audible.
Yeah, I just wanted to mention that the biggest challenge which I used to face as the chief executive was finding ways and means of storage of heavy water. The production was so large and the storage capacity every now and then we have to find out new ways of storage. I hope that problem is no more there, but no doubt you are still producing and you must be having a large storage and much more storage may be required. How are we solving that problem?
No, this problem, sir, still exists, and we have taken the as a capital scheme actually. Now
Can't hear anything.
the many numbers of large storage we are separating, but the nuclear reactors are coming in a very slow pace. This problem still exists.
Sir, did you hear that? Did you get that? I think, sir, I'll share a video with you subsequently where you can maybe capture whatever has been spoken in this. Because there seems to be some audio problem at your end.
Very faint voice is coming.
Yeah, so I'll share a video with you of the entire proceedings.
May I cut in a little bit? I see one question from somebody, and that was also asked in my talk. I don't know who is asking the specific energy. May I go ahead?
Yes, sir, please.
The specific energy consumption for G2O production decreased from 44 gigajoules per kg to 27.9 gigajoules in 2014-15. But in 2020-21, it again increased to 30.2. As with the why this rise? I think somehow it has been missed by Mr. Srivastava, not taken it up. The point is, this energy consumption figures that have been given are the average for all the plants taken together. Some of the plants have one specific energy consumption and another one based on another process and got another one. So some of the variations have come in when some plant has been taken out of line, and also with some aging of the plants. These are the two reasons why there's a small hike. That's the explanation I wanted to offer. Over.
Sir, this 27.8 actually, as such, ammonia plant specific energy is much lesser than the sulfide process. It comes around 25, between the 25 and 26. Once the ammonia plant are operated fine, their contribution is higher as compared to the sulfide plant. Then this type of this variation, because this is the combined specific energy of the both ammonia and this, because this it is around 30 gigajoule average, but still our sulfide plant are running between 30 to around the gigajoule.
So different plants have different thing, and their performance and their being online and annual turnover being taken in some year. So that brings in some kind of variation. And plus some aging also. Energy consumption goes up a little bit.
Mr. Srivastava, there are a couple of questions. The present cost of heavy water for consumers other than DAE. There's a question from Santosh, Mr. Santosh. And Mr. Sanjay Kumar of AMD wants to know, apart from PET scanning, what are the other uses of O18 water?
Present cost of heavy water is around 30,000 rupees per kg for the normal market. And many people are buying for non-nuclear field from us.
Okay. And other uses of O18?
O18, we have got one is the PET scanning is used S2O18 of 95.5 95 plus %, and 10% we have got some demand from this they require the metabolism study for the people who are living at a high altitude like Siachen and all. DRDO actually 10% to 18 is required for their metabolism study. That two uses we know for 10% and 95% for the PET scanning.
Okay. There is a question, which is a better moderator, D2O with O16 or D2O with O18?
In my opinion, sir, which I read in the training, D2O16 is better moderator than D2O18.
Okay. Then there is a question of why the production of enriched O18 has been delayed. Of course, I think you already answered that in your talk.
We have not delivered actually. The amount is very less, and we require good amount of for the purification actually.
Okay. Okay.
It will take around 6 months to deliver for the use.
Okay. 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 Then there is a question. So what is the present cost of O18 for 95% purity?
Actually, that we are working out, but the initial working, whatever we have, it is competitive in the international market, sir.
Okay. Okay. There are no more questions, but there are a lot of messages complimenting you on your presentation. So I convey I'll convey on behalf of all of them my congratulations to you for making an excellent presentation. I don't see any other questions right now. So Ramarao, shall I hand over to you?
Yeah, let's request Malhotra to give vote of thanks.
Yeah.
Malhotra ji.
Yeah, thank you very much. So friends, I think you all will agree with me that today we heard the saga of heavy water. And at least, I mean, I am 100% sure it must have made proud all of you. I can tell you about my personal experience. I had joined in 1977 after passing out from training school. And every year I will go for that Founders Day lecture, you know, which will be held on every 30th October. So I will, every year I will attend that lecture, and I used to listen to the progress in various DAE things. And, you know, I was in heavy water division. So in a way, I was part of the heavy water program. So up to, I think, mid 80s, every year there used to be a line, only one statement that, okay, Heavy Water Board is trying very hard to start production of heavy water, and someday we will be self-sufficient in heavy water. So that kind of statement used to come, and I used to feel, you know, very bad. And then in the 90s, as Mr. Kamath just now mentioned about the problem during his tenure as CE, in the 90s, this statement about heavy water, every year will be told that now heavy water board is facing a different problem. There is a storage problem. There is so much heavy water that we are finding less place to store. So this says the entire success of the heavy water board. And now about the diversification activities. In fact, when I was working at DAE, I many times, as Dr. Manchanda told that the name of heavy water board should be changed, I indeed suggested to Dr. Kakotkar seriously that you name heavy water board as the chemical engineering board of Department of Atomic Energy. And in a lighter mode, I told him that you name heavy water board as a kuch bhi mango board. You know, you ask for anything and heavy water board will deliver. Another name I had suggested, again in a lighter vein, that Vardhan Mango Board of Department of Atomic Energy. So, you know, these are the kind of things. Anyway, I think I am drifting away. So my compliments and my congratulations to Jitendra Srivastava for a wonderful talk. And I always say a talk comes when you speak with conviction. And you can speak with conviction when you are backed with success. So I think I should not only thank you, so many seniors are present here. And even if they are not present here, I think all the leaders of Heavy Water Board, as just now Sharmaji mentioned about Mr. Khillani, that he is the father of O18 technology. So, and I think today we are reaping the benefit of that. So I think all the leaders and all the contributors to Heavy Water Program, along with Jitendra Srivastava, I thank all of them. And I only have one sentence to say, that you have made us proud and continue this wonderful saga. Now, I also thank our president, Shri S.K. Mehta, and the entire executive committee of INS for supporting this webinar program, which is, you know, I think the next webinar I can announce that it will be Sweet 16 webinar of INS. So today, 15th one has been delivered. So now it has found firm roots, and I think every month we are having 2 webinars. Fantastic. So thank you very much, especially to the webinar subcommittee, whose convener is Mr. Ramarao and his colleagues. I thank them and compliment them for making the webinar program so smooth. I also, like every time I do, I thank our Shri G.D. Mittal, part of our team, INS team, and Dr. Shimjit Rajgopal of BARC, who tirelessly, every time there is a webinar, they contribute for propagating the information about the webinar to largest number of people. And they are continuing to do that job. And then finally, I thank all the audience which were there in good number, and for the patience and for taking the trouble that on a weekend you are coming and giving your time to listen to this webinar. And I think in that I can particularly mention Dr. Rathi, all the way from Dallas, USA, at 5:30 in the morning. He has joined us, so thank you very much. And you can force some other friends also. See, we have a heavy water group, so you could have forced some of them who are there in USA. Large number of heavy water guys are in USA. So anyway, my compliments to all the audience who were here, and for a lively discussion session, particularly after the seminar. I thank everyone. And before handing over the mic, as I do every time, I have the pleasure of announcing the next webinar, which will take place on 19th February, and another success story you are going to listen from Dr. Asnani, Chairman and Managing Director of Uranium Corporation of India Limited. And his topic, naturally anybody can guess, his topic will be uranium ore mining and processing for energizing the front end of the nuclear fuel cycle. So expect you on 19th February in large numbers. Thank you. And with that, I sign off. Thank you very much.
Thank you. Thank you, Malhotraji. Thank you very much. And I think we profusely thank Jitendra Srivastava for having taken over the department and the water board. And many people who joined, we are delighted to have you on this platform. We promise to bring newer and more vibrant discussion in this webinar. So I thank everybody. And before we close, I request Ramanamurthy to stop the recording. Thank you. Thank you, everybody.
Thanks.
Thank you.
Thanks.
Thank you, sir.